Hello students, welcome to Marine Engineering Tutorials. I'm Atul Kumar Gupta and I'm back with a new tutorial. We are currently studying marine boilers. Today we will begin our fifth lecture on marine boiler fundamentals, and the topic for this session is heat transfer in boilers. First, we will discuss the three modes of heat transfer: radiation, convection, and conduction, and understand how each operates within a boiler. Next, we will look at the flow of fluids inside boilers, focusing on the parallel, cross, and counterflow arrangements. Then we will compare the advantages and disadvantages of parallel and counterflow systems. After that, we will learn about the conditions for maximizing heat transfer through conduction, including factors like surface area, material thickness, and tube design. Finally, we will examine the design considerations required to manage stresses in high pressure boilers without compromising safety or efficiency. Let's now go through each of these topics one by one in the following slides. Heat transfer in boilers. A boiler is a heat exchanger in which water receives latent heat to produce saturated steam, which may then be further heated in a superheater to receive sensible heat and become superheated steam. Superheated steam may be desuperheated again for auxiliary purposes, while waste heat is recovered to preheat feed water and combustion air. Modes of heat transfer in boilers. A boiler utilizes all three modes of heat transfer, that is radiation, conduction, and convection, which are being discussed here. Radiation. Heat transfer through radiation is the process by which energy is transferred in the form of electromagnetic waves, primarily as infrared radiation. In boilers, radiation heat transfer occurs from the burner flame to the furnace or valves. Unlike conduction and convection, radiation does not require a medium to transfer heat and can also occur in a vacuum. Radiation heat transfer follows the Stephen-Boltzmann law, which states that the total energy radiated per unit surface area is proportional to the fourth power of the absolute temperature of the object. Mathematically, Q is equal to sigma epsilon A T to the power 4, where Q is the radiant heat energy emitted per unit time in watts. Sigma is the Stephen-Boltzmann constant, whose value is 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. Epsilon is the emissivity of material whose value varies from material to material, and for rough and dark steel surface it is 0.6. A is the surface area in meter square, and T is the absolute temperature in Kelvin. Heat transfer by convection. Convection is a mode of heat transfer that occurs in liquids and gases when their particles move physically from one place to another, carrying energy with them. In boilers, the flue gases from the furnace transfers heat convectively to the tubes, which are either surrounded by water or have water flowing through them. Newton's law of heat transfer by convection states that the rate of heat transfer by convection is directly proportional to the surface area, the temperature difference between the surface and the surrounding fluid, and a constant of proportionality called the convective heat transfer coefficient. Mathematically, Q is equal to H into A into delta T, where Q is the rate of heat transfer in watts, H is the convective heat transfer coefficient in watt per meter square, which depends on the nature of the fluid and flow conditions, whose range is for flue gas between 5 to 250 to 200, for water in natural circulation between 100 to 500, for water in forced circulation between 500 to 10,000, and for steam between 200 to 1000. A is the surface area over which heat transfer occurs in meter square. Delta T is the temperature difference between the surface and the fluid, which may be in Kelvin or degree Celsius. The rate of convective heat transfer is influenced by the temperature difference, the properties of the fluid such as viscosity and thermal conductivity, the speed of fluid flow, and the surface area over which the fluid moves. Heat transfer by conduction. Conduction is a mode of heat transfer that occurs within a solid material or between substances in direct contact, where thermal energy is transmitted through the vibration and interaction of atoms and molecules. Heat transfer through conduction is governed by Fourier's law, which states that the rate of heat transfer through a material is directly proportional to the temperature gradient and the cross-sectional area, and occurs in the direction opposite to the temperature gradient. It is mathematically expressed as Q is equal to minus K into A into delta T by T, where Q is the rate of heat transfer in watts, K is the thermal conductivity of material, typically 15 to 60 watts per meter for steel. A is the surface area of heat exchanger in meter square. Delta T is the temperature difference in Kelvin or degree Celsius. And T is the thickness of material through which heat is conducted in meters. Heat naturally flows from a hot region to a cold region. A larger temperature difference results in greater heat flow. Materials with higher thermal conductivity K conduct heat more efficiently. Metals conduct heat far better than insulators. Extending the surface area using fins or gills enhances heat transfer by increasing the effective area for conduction and convection. Direction of fluid flow in boilers. This sketch illustrates the flow of fluids in different types of heat exchangers used in boilers. In boilers, the flow of one fluid, either flue gas or water or steam, takes place through the tubes while the other fluid flows around the tubes. Circular tubes are generally preferred in boilers because they provide maximum strength compared to other shapes. Although they offer the least surface area for a given volume whose value is 2 pi r L. Parallel flow. In a feed water heater or economizer, the two fluids, water and flue gases, usually have parallel flow. That is, they flow in the same direction. In a parallel flow arrangement, the large temperature difference at the inlet ends can cause significant thermal stresses, which may eventually lead to material failure. Additionally, the exit temperature of the cold fluid can never exceed the lowest temperature of the hot fluid, which is a disadvantage in applications such as boiler, where maximum heat recovery is desired. Cross flow. In the generating tubes, water and flue gases typically have cross flow. That is, they flow perpendicular to each other. Counterflow. In the superheater tubes, steam and flue gases generally have counterflow, that is, they flow in opposite directions. Compared to parallel flow, counterflow is more efficient. It provides a more uniform temperature gradient which ensures better overall heat transfer, maintains a consistent rate of heat transfer, and minimizes thermal stresses. In a counterflow arrangement, the outlet temperature of the cold fluid can approach the inlet temperature of the hot fluid. However, maintaining such conditions often results in high mean metal temperature, which require high-grade material. Although counterflow has several advantages over parallel flow, boilers mostly use parallel flow due to safety and reliability considerations. Comparison of parallel and counterflow. This figure compares the temperature profiles of parallel flow and counterflow heat exchangers. Each flow arrangement has its own advantages and disadvantages as discussed here. In a parallel flow arrangement, both fluids flow in the same direction. The large temperature difference at the inlet end can cause significant thermal stresses which may eventually lead to material fatigue or failure. Moreover, the exit temperature of the cold fluid can never exceed the lowest temperature of the hot fluid. This is a major limitation when the objective is to achieve a substantial temperature rise of the cold fluid as is often required in boiler applications. In a counterflow arrangement, the two fluids move in opposite directions. This configuration produces a more uniform temperature gradient, resulting in improved overall heat transfer efficiency, a more consistent rate of heat transfer throughout the heat exchanger, and reduced thermal stresses across the system. The outlet temperature of the cold fluid can approach the inlet temperature of the hot fluid, providing higher thermal effectiveness. However, such designs often lead to higher mean metal temperature, necessitating the use of high grade materials to ensure structural integrity and durability. The precise temperature difference between the two fluids across a heat exchanger is best represented by the log mean temperature difference LMTD, which can be expressed by the equation LMTD is equal to delta T1 minus delta T2 divided by natural log of delta T1 divided by delta T2, where delta T1 is larger temperature difference between the two fluids either at inlet or outlet. Delta T2 is smaller temperature difference between the two fluids either at inlet or outlet. It is important to note that the temperature variation across the heat exchanger is non-linear. Therefore, heat exchangers are designed to achieve maximum heat transfer efficiency while ensuring operational safety, material reliability, and long service life. Conditions for maximizing heat transfer through conduction. High temperature difference. We have learned that heat transfer is directly proportional to the temperature difference between the two fluids. This difference can be enhanced by adopting a counterflow arrangement where the fluids move in opposite directions to maximize temperature gradient across the heat exchanger. Large surface area. Heat transfer is also directly proportional to the surface area available for exchange. The effective surface area can be increased by using fins or gills. However, from strength and pressure resistance perspective, circular tubes are preferred in boilers, although they provide the least surface area compared to other shapes. They offer maximum mechanical strength. Sinusoidal or corrugated tubes are sometimes used in heat exchangers to improve turbulence and heat transfer efficiency, but they are more difficult to clean and maintain. low wall thickness. Heat transfer is inversely proportional to the wall thickness of the heat exchanger. Therefore, the tube wall thickness should be kept as thin as possible while still providing adequate strength to safely withstand the internal and external pressures during operation. Design considerations for managing stresses in high pressure boilers. Circumferential stress sigma is equal to PD by 2T. We have earlier studied that the internal steam pressure acting on the drum walls induces a large stress known as circumferential or hoop stress, which is mathematically expressed as sigma is equal to PD by 2T. Stress sigma is proportional to P. As the boiler pressure increases, the stress on the drum wall also increases. Stress is inversely proportional to the thickness. Since the stress is inversely proportional to the wall thickness, the shell thickness is increased to withstand higher pressures. Because the boiler drum is not directly involved in heat transfer, its greater thickness does not affect thermal performance. However, in smoke tube and low pressure water tube boilers, the furnace walls are surrounded by water which participate in heat transfer and is also subjected to the pressure stresses. Hence, these boilers cannot be used for high pressures as increasing the furnace wall thickness would reduce heat transfer efficiency. Stress is directly proportional to diameter. Since stress is directly proportional to diameter, large capacity, high pressure boilers are designed with a higher length to diameter ratio to reduce the drum diameter and limit the resulting stresses. Conversely, the furnace of smoke tube and low pressure water tube boilers should be made compact to minimize stresses. When a high rate of evaporation is required, multiple small furnaces may be provided instead of single large one to limit the diameter and maintain mechanical integrity. Thus, thickness is directly proportional to the diameter. Since the required wall thickness is directly proportional to the tube diameter, smaller tube diameters are preferred for efficient heat transfer and lower metal temperature. In medium and high pressure water tube boilers, the furnace is surrounded by tubes containing water known as water valves. This arrangement removes the size limitation on the furnace as the heat absorbing tubes effectively withstand pressure and transfer heat simultaneously. A typical water to steam ratio of 5:1 to 10:1 is maintained during boiler operation. Therefore, the tube diameter should not be smaller than 40 millimeter, that is 1.5 inches, to avoid a low water to steam ratio, which could cause tube overheating and failure. This completes our study of modes of heat transfer in boilers, flow directions of fluids in various heat exchangers, comparison of parallel and counter flow, conditions for maximizing conductive heat transfer, and design considerations for managing stresses in high pressure boilers. This book has been written by me and covers all the topics as per the Indian Maritime University syllabus. It explains key concepts using simple illustrations. The book also includes answers to all questions that have appeared in examinations conducted by Indian Maritime University. It will help students prepare effectively for exams and also support them in working safely with ships' boilers. I hope you enjoyed the lecture. Feel free to share your feedback in the comment section. If you found the tutorial helpful, consider sharing it with your friends. Subscribe to the channel to stay updated with upcoming tutorials. I'll be back soon with a new lecture. Thanks for watching till the end.